today Rong-Gen Cai. He's going to talk about condensation of vector field and holographic model of P-wave superconductor. So please.
Okay, thanks. This all need to thanks organizer for invitation so that I have chance to visit Cambridge. In my mind, Cambridge is something like the science Paris. So it's a really good place to spend. I have a very pleasant time here. Thanks, particularly Antonio. Today, I will talk about the condensation of the vector fields from the holographic viewpoint. This talk is mainly based on two works with my student, PhD student Li and postdocs He and Li. Li will graduate next year, and Dr. Sun will join the Yoko Institute next month as a GSPS fellow. And Dr. Li, he just got a position in the Center for Space Science in the Chinese Academy of Science last month. Okay. This is the outline of my talk. After a very brief mention of the motivation of my research, then I will present our model. Basically, this is the Einstein-Maxwell complex vector theorem with in the ideal space. Actually, after the numeric solve the model, we found the system contains a very rich phase structure. Depending on the mass of charge of the vectors, we found the second order, first order, and the zero order phase transition is the same. Particularly, also the retrograde condensation also happens in some region in this model. Oh, this one. Yes, I will mention that. Okay. In the third part, in the traditional superconductor model, the magnetic fields usually destroy the superconductivity. However, in our model, the vector condensation could be induced by the applied magnetic fields. This is mainly due to there is a non-minimal coupling between the vector and the background magnetic fields. That is the conclusion. Our motivation of this study is twofold. One is motivated by the research on condensation of the charged low mass in QCD in very, very strong magnetic fields. And another motivation is to build the P-wave superconductor model in the holographic viewpoint. Let me first mention the first point. Recently, there are a lot of works to study the property of the QCD vacuum in the very strong magnetic fields. The main reason is that people believe that a very strong magnetic field could be collected at a Racker or the LHC experiment, particularly in the QGP phase. It is said the magnetic field can reach around this range. Here, m pi is the mass of the pi meson. Roughly, this value could reach to the 10 up to 6 Tesla. Very, very strong fields. Such kind of things, of course, could not be seen in the ordinary environment, but can be seen in the the QGP phase or in the very early universe, or in interior of the strong stars. In such kind of very big, very huge of strong magnetic fields, then the vacuum of the QCD will be changed. It is said the QCD vacuum will undergo the phase transition to a new phase where charged low mass are condensed. Actually, in the QCD theory, the low mass is very short-lived. He will very quickly decay to the pi meson. However, in the strong in a magnetic field, here is the mass of the pi. This one is increased with the magnetic fields. However, the mass of the low meson is decreased with the magnetic fields. When the magnetic field reaches this point, then the low meson tend to be a tachyon. So in this case, condensation happens. So in this case, QCD vacuum in a very strong field is nothing but like the superconductor. This is one motivation to others. But you know, such kind of region actually in the very low energy of the region of QCD. In this case, we need to use the Sichuan coupling theory. So here ADS-CFT is applicable. In a very Maxim Chernobyl in this paper, he used another point. Such kind of low mass condensation in QC cell behavior is very like the other point, like for example ground condensation in the very strong magnetic fields. But this is the magnetic fields is not the Maxwell one, but the color magnetic fields. And also like the double boson condensation in the electroweak theory, also in the very strong magnetic fields. Such kind of condensation happens. The crucial point is that is the existence of the very large ground magnetic ratio for these particles. The three condensations actually behave very similar. This is from the point of view from the particle physics. And then Maximum used the effect theory of low meson to study the condensation of low meson. Then the model he used is called the DSGS model. And the four persons proposed in this paper. This is, of course, is effective description of the low meson electrodynamics. Here's the contents. Here is the Maxwell fields. Low mu is actually charged low mesons. And this is the mass term. Here, rho naught is defined here. Which one? This one is a neutron low meson. And this is the mass term. Particularly, there exists the non-minimal coupling term, this term. This term can turn into, can be composed in two parts. Actually, this term describes the magnetic moment of the low meson to the coupled to the background magnetic fields. These terms play the crucial point for the low meson condensation. Use this is the very the effective theory and the maximum found. When the electromagnetic fields reach to the point, then the condensation happens. This is the profile of the condensation with respect to as a function of the applied magnetic field. Along this point, then the condensation happens. The condensation increases with applied the magnetic fields. And also, the Ablikosov vortex lattice also could be realized in this model. Here is the profile, and here in the plane of x1 and x2. There is a magnetic field which is perpendicular to the plane of x1, x2.
But these results are obtained from holograph, right?
Yes, this is from the effective theory. Totally is from the field theory. Yes.
And you are somehow in order to the results in some kind of weak coupling limits, right?
Oh yeah.
Yeah, because this is an effective model.
Effective model, not from the QCD model. Yes. Another motivation is to build the holographic model of a P-wave superconductors. According to the CFT ADS dictionary, to build a P-wave superconductors, then we need to replace here. Okay, first mention that. Suppose we want to have the phase transition in the field theory side. Then, in the gravity side, we need to introduce abelian gauge fields to describe the global symmetry in the superconformal field side. If the phase, the order parameter is a scalar operator, then we need to introduce the scalar fields in the bulk. Because the phase transition happens at finite temperature, then we need to look for the black hole solution. To mimic the phase transition in the conformal field side, we need to find a solution of a black hole solution, which is no here, no scalar here, or other vector or something else. Is a high temperature region. When the temperature decreases, the black hole solution with no hair turns to be unstable. Their stable solution with hair appears. From the black hole without a hair to the black hole with a hair, such kind of process could be explained as the phase transition in the conformal field side. If we need to introduce a p-wave superconductor, then in the book we need to introduce p vectors, complex vectors. Of course, as you know, there is a p-wave superconductor model, holographic model, introduced by Gobus and Prof. Amon and his collaborator consider back reaction. In this case, the order parameter is a vector. The Gobus and Prof's model describes this action. Here R is the scalar curvature, and this is, of course, negative Cosma constant. Here is SU2 gauge fields. Working in the probe limit, it means the back reaction of the mat sector is negated. In this case, you have the ADS Schwarzschild black hole solution. This is the way. RH is the horizon of the black hole. Then make the answers in this one. Choose the one subgroup of the SU2, for example, as the Maxwell fields in this one. Then consider another subgroup here. If the omega R does not vanish, then the U1 symmetry is broken. So in this way, to explain the phase transition in the superconductors. In the probe limit, these two functions satisfy these two equations. From this equation, you will see very clearly. Once this term does not vanish, then the phi has not the U1 symmetry associated with this subgroup is broken. Here is the condensation behavior of the vectors. Here the critical point, the dual operator vanishes like in this way. The critical explains just the 1/2, just the value in the mean fields. Here it shows the ratio of the superconductor charge density to the total charge density. When the temperature goes to 0, this is one reach to the 1, this ratio. Okay.
What is the parameter?
Other parameter is just this one, the vector omega. This is the story about in the probe limit. Once the back reaction considered, something is change happens. Here alpha measures the strength of back reaction. When alpha small, then this condensation is clear. This is okay. Second order phase transitions. When alpha increase beyond to the critical value, for example, here shows the alpha equal to the 0.447, then the condensation behave like the multi-value. This one shows the phase transition turn to be the first order phase transitions. To see this, we need to calculate the free energy and entropy. This is a small back reaction case. This dashed line describes the RN ADS black hole, which is the normal phase, described as the conductor phase. And when temperature reaches to critical, this blue one, this is the green, this is the red one, is the new black hole solution with the condensation. So from this is the entropy. So the entropy is continuously, but its slope has a jump here. So in this case, the phase transition is second order. And when the alpha increases, here a typical swallowtail appears. It's typical signal for the first order phase transitions.
Can you explain again what is alpha?
Alpha is the yielding constant over the coupling constant of the SU2 gauge fields. Measures the back reaction of the matter fields.
So it measures back reaction.
Yeah.
So with no back reaction, you have always second order phase transition.
Yes. Without the back reaction, then it's just this.
Okay.
Okay, this is the story for the SU2 p-wave superconductor model. Okay, Now we present our model. The model is simply just the DS, in some sense like the curved version of the GS model. Okay, this is the Einstein-Maxwell complex vector theory. Here, of course, this is the gravity part and this matter part. And we neglect the part for the neutron mesons because that component is not relevant. Now we can, in this part, we first neglect this the non-minimal coupling term because in this case, these terms are not relevant. So the ansatz we adopt is this one. We consider the back reaction case. This is the matrix. We introduce three functions, F, chi, and H. And this is the Maxwell fields ansatz. This is the vector part. We just choose X as a spatial. And in this case, the isotropic symmetry is broken also because, this is the vector. We choose around this direction. So we introduce the H function to describe the any isotropicals in the XY plane. Okay. With this ansatz, then the equation motion turn to be this one. This is a four coupled equation motion with 5 equations. Now the problem is to solve this equation with the suitable boundary condition. One boundary condition, okay.
With or without the non-minimal coupling?
Non-minimal coupling, yes. I will show the law of this term in the third part. Okay, here because with this ansatz, because there are no background magnetic fields. In this case, this term plane no any law. Okay. So this equation turn to now we solve the numerical solve this equation with the suitable boundary condition. In the horizon, we of course all fields should be finite. Then at the ADS boundary conditions, the electrical fields behave like this one. Here mu, of course, mu and rho, according to the ADS safety dictionary, could be explained as chemical potential and charge density of the conformal field cell. And the vector part, we have two terms. Delta minus and delta plus are dimension of the operators. Is given this one. Since we want to the symmetry, U1 symmetry is spontaneously broken. So according to the ADS safety dictionary, this term is a source. So we drop off this term. Set this value equal to 0 when we solve the equation motion in the ADS boundary. Then the three matrix function behave like this one in the ADS boundary. Here F3, H3, and Chi3 are constant. So please notice there exists 3 scaling symmetry in the equation of motion. There are 3 scaling symmetry. Take this one. We could set horizon equal to 1, this chi equal to 0, and H equal to 1. Okay. This is with this is the 3 scaling symmetry. Then after numerical solve the equation of motion, we could use such kind of scaling symmetry to make the solution with the correct asymptotic behavior ADS boundary. Of course, in the previous equation motion, there is a special exact solution. This is nothing but the R and ADS solution. Describe this one with the trivial vector profile. This is nothing but just the normal phase without the condensation. Because in this set there are many solutions. To see which solution is thermodynamically favored, we need to calculate the free energy of the black hole solutions. Okay, this is nothing but just the given. We work in the ground canonical ensemble. So it means the chemical potential is fixed. In this case, the free energy is just Gibbs free energy. This is temperature, this is Euclidean action of the theory. Take the equation of motion, it turns out the free energy is very simple, given by three volumes in the matrix expansion. What?
Yes. What is this entropy?
Entropy. Oh, entropy is entropy. Okay, I will show. Entropy is nothing, just to satisfy the area law of the.
No, this is action.
This is this is like Euclidean action. Yes. This is Hawking temperature. Yes, right. And V2 is the area of the transverse direction. Okay. We knew through the numerical calculation, we find the system behave qualitatively different when the mass, okay, larger than this one or less than this one. The critical value in the numerical control system, the numerical one, something like that one, very close to 0. If this one MC square equal to 0, then the operation dimension just the 1, isn't it? This is very special. So the system, we divided the system into two parts. One is case with larger than the critical one, another is less than this one. For the first case, when the mass of the vector field is larger than the critical one, as an example, we consider this one, m squared equal to the 3/4. This take this value just for the convenience of the numerical calculation. Other values behave similar. Now the only parameter is the charge Q of the vectors. In this case, we find there exists a critical value of the charge. For this value, critical charge equal to 1.3575. Then the charge, if larger than this one or less than this one, they also behave different. If the larger than the critical one, take example, for example, Q equal to 0.5, then this is the condensation of the vector fields. Very simple. This is the second order phase transition, very clear. Same as the SU2 model. This is the free energy, this is the entropy. The dashed line, or the described as the R and ADS case. This blue, this is the red one, described as the black hole is here. This is the entropy, this is the condensation. The condensation, when the temperature goes to 0, the condensation goes to finite value. So, particularly from this figure, you can see where the temperature goes to 0, the entropy is extremely tiny, which means this is the solution, extreme solution, is not the extreme RN ADS case. RN ADS case, you know, when the temperature goes to 0, the entropy is finite. So in that case, so it means usually in the traditional materials, when the temperature goes to 0, the entropy should go to 0, right? So this system, the behavior is quite different as the RN ADS case. Now when the Q is less than the critical value, take example, for example, take the 1.2 case, then the condensation behaves the multi-volumes. This is, of course, this is just the first order transitions. To see this, we calculated the free energy. A typical the swallowtail appears here. Here, this is again this RNADS black hole. When the temperature reaches to this one, then the system takes this branch, and there is a jump of the entropy from this point, typical to jump to this point, then goes to is also approach to very tiny entropy. So this is the phase diagram. This is take example m squared equal to the 3/4. This is the second order phase transition region. This is the red one is for first order transition. This is the critical temperature, which depends on the charge Q. Now, very interesting case is the m squared less than this one. As an example, we consider that this value m squared equal to -3/16. in this case, we find the charge of vector divided into 3 regions. One is larger than Q alpha, another is less than Q beta. Another region is between of them. Of course, Q alpha and Q beta depend on the value of the mass of the vectors. In this case, we found the Q alpha equal to this one, Q beta equal to this one. So let's first see this first case. When the Q larger than Q alpha, when the temperature is low, reach to the, for example, here, then the condensation happens. If you continue to lower the temperature, then you find condensation will, there is a minimal temperature around T0. The condensation turns back to the high temperature case. So in this case, you have the 2 branches for the condensation. Clearly, this above branch is unstable. To see this very clear, to see this is the free energy. You will see this is the dashed line also for the Rn ADS case. Here, the second order phase transition happens here. When reach to the minimum temperature, the free energy turns back to this one. So this branch, of course, the free energy is larger than this one. So the below one is stable, above one is unstable. Here is the charge density behavior. This Rn ADS black hole, when the phase transition happens, the charge density increased till to the minimum temperature, then turn back. This here is entropy. There is from this point, it goes around this branch to the minimum one. So if you continue to lower the temperature beyond the T0, then what will happen? Because the less than T0, there only one phase appears. It's nothing but the Rn ADS black hole. So if the condensation reach to this temperature, the system must be from this point joined to the normal case. In this case, free energy has a jumper. According to the definition of the phase transition, then this is the 0 order phase transition. Here I have 2 comments. So you will feel very strange because usually we do not study the 0 order phase transitions. We look at we check out the reference. We found there is a paper discusses this one, 0 order phase transition, published in the mathematical notes here. In this paper, the author discussed the 0 order phase. It argued that such kind of 0 order phase could happen in the superfluid or superconductor model. He presented a solvable model to show these properties. Actually, such kind of behavior, 0 order phase also happens in 5-dimensional gauge supergravity in these papers. This paper also built the P-wave model, but with the 2-form fields in the 5-dimensional supergravity. Yeah. Such kind of phenomena also appears there. If the charge is less than between them, take example, for example, Q equal to 39 over the 40, then the branch, the condensation branch, you will have 3 branches from this point to here, and this here to this one, this turn back. Of course, only one of them are stable. Another 2 branches are not stable. But the minimal temperature is still there. This is the free energy. So if you lower the temperature, first is Rn ADS black hole. Here you have the first order phase transitions. Condensation happens. There is a jump to 0 to this point. So around this line, turn to due to the minimum temperature, then it turns back along this branch. This branch, of course, is unstable. This is stable. Once again, if you continue to lower the temperature, this point has to jump to this one. This is also the 0 order phase transition. Here is the first order phase transition. This is the charge density behavior. Also, you have the 3 branches. This is the entropic case, entropy case. So in the third case, the Q is less than Q beta case. We take the two examples. One is Q equal to 19/20, another is 9/10. You will see their behavior different. Here, condensation happens in the high temperature region, not in the low temperature region. The condensation increased with the temperature. In this case, the condensation behaves a multi-value case, but here is automatic increase. So here is shows the charge density, and this is also charge density. Here also the multi-value case. The multi-value behavior is nothing but just shows there is a first order transition, actually. So to see this, we show the entropy and the free energy. This is the dashed line described as R in ADS black hole. And entropy here is okay, behave like this one. With the black hole with the condensation, behave like this one. Here is the automatic with this charge case. Here is the free energy. You will see the free energy for the black hole with condensation is always larger than the R in ADX case. So this phase is metastable or unstable. Here in this case, there is a typical swallowtail here. Here is nothing, but here look like the second order phase transition here. Of course, in the phase diagram, such kind of phase could not appear because this is unstable phase. But such kind of case, in the residual situation, such kind of case also will happen. Here I have two comments. Such kind of the condensation happens in the high temperature rather than it's called the retrograde condensation. Actually, this was first introduced to describe the behavior of a binary mixture during the iso completion above the critical temperature of the mixture. It seems this is the first reference to mention such kind of thing in the very, very old times. Such kind of various change behavior actually in some models also appears. For example, in this model, in these papers, Birch and Bergnetti, it's called the exotic hair black hole in this paper. In their paper, they are introduced two scalar fields with designed the theory. So such kind of behavior, condensation happens in the high temperature rather than in the high. Also, in these two papers actually is the truncation of the low energy of the supergravity in the 5-dimensional or the 4-dimensional. So such kind of retrograde condensation happens in the string theory model.
But is there any simple argument to understand that? Why a system that you are just heating and goes above the critical temperature, condensate precisely above some critical temperature, not below?
Yes. In this paper, those papers actually they are no give any the physical explanations, but I think this is very mainly related to this interaction, various change interaction term in the theoretical model. In the holographic models, such cases actually depend on the dimension of the oplet.
Okay.
Yes. Probably such kind of oplet, I think maybe violate the unitary condition.
And did you compute things like conductivities or something like that?
Yeah, this one conductivity is not yet calculated in this model. Yes. Yes. Here is the phase diagram. Shows the mass equal to this case. You have the three regions. This region and this region is nothing but the R in ADS normal phase. Here is the second order phase transition, and this is zero order phase transition. This is the one. And the later part, this is the first order phase transition. This part is the zero order phase transition. If the Q less than this one, then this is just the regulated condensation happens. So this is the case with the with this mass case. And this is the first line with temperature with respect to the mass squared. We take the Q equal to 2 case. Here, this line describes the critical temperature for the second order phase transition. And this one describes the zero order phase transition here. Here's the mass squared. Now I move to the third part, the vector condensation induced by the magnetic field. Mainly consider the effect of this term, because in this case, we will add the external magnetic fields. In this case, we work in the probe limit. Then the background is chosen the Rn is the Schwarzschild ADS black hole solution. RH is the horizon of the black hole. A consistent answers taken in this way. Here we introduce the small filament with a derivation filament, which just describe as little bit above the condensation. Okay. And this is the Maxwell fields, electro potential, and introduce the magnetic fields in the XY plane. B. This is the zero order. And the condensation happens the first order. Here P is constant. Y, of course, is coordinate. And we also introduce the phase of the rho Y. Theta is a constant. Of course, at the zero order, the Maxwell fields, the potential satisfies this one. Of course, you have the solution here. Mu is nothing but the chemical potential. Okay. Then, at the linear order of this model, we could get the equation motion for the rho x and the rho y. We assume the rho x and the rho y have such kind of the form. Means the wave function could be separated along the x and the r direction. In this case, we found that the phase theta only can be taken two values. Theta plus equal to pi over 2 with this number, 2 and pi. And theta minus is this one. And here is integer. Only two values are allowed. Otherwise, the system are not consistent. In this case, the equation motion turns to be that one, phi x and this one. And then to solve this equation motion, we assume phi x and phi y, there is a linear relation. Here, theta is a real number. In this case, this equation turns to be this one. And also, this constraint is automatically satisfied by this equation. With such kind of assumption, we can solve these two equation motions. Here, this equation, the upper sign corresponds to the theta plus and lower ones to the theta minus case. Okay, now we have the three equation motions. Here, E is the separation constant. Of course, we can solve the equation motions. The result is that I do not show the full result here. Two crucial points is that the eigenvalue of the separation constant, eigenvalue is turned to be this one. N is integer. Okay, C is a constant. Another crucial point is we see the effective mass of the phi x behave like this one. Here's the eigenvalue, and this is a contribution from the Maxwell fields. So the magnetic field has some contribution to the effective mass of the phi x. In the below, we just consider the lowest lambda level state. In this case, we take n equal to 0. In this case, the eigenvalue turns to be this one. The energy is minus 1. Is just this term totally comes from the non-minimal coupling term. And the solution x naught and y naught are given by this one. N naught here is normalization constant. This is finite, like the drop solution in the superconductors.
This constant C.
Oh, constant C. Here, C, right? Is yes. Basically, this is the arbitrary constant. But okay, when we solve this equation, make then C squared equal to 1.
Comes out of the equation.
Yes. Basically, this is arbitrary real constant. But if for the arbitrary constant case, the C, this equation, we are not sure this equations of motion are solvable or not. But we got the solution when the C squared take to 1 case. I think this solution is consistent with the condensation of low mass in the effective field theory. They are consistent. So we take C equal to 1. We think this is consistent. Yes. So now we consider the lowest lambda level state. In this case, the effective mass of vector fields behave like this one. Crucially, the contribution is negative. So in this case, when increase the magnetic field, the mass square will turn to negative, turn to some of the critical value. In this case, the condensation of vector happens here. So even this term is vanished case. So there exist two different cases without a charge density. So the last term vanished case, or with last terms. So let's first consider first case. In this case, the equation motion for the phi x turn to be this one. Here we introduce the coordinate z. Z is defined as this one, and theta is defined as this one. The magnetic field over the temperature square. Now we solve this equation motion with the boundary condition. At the horizon, of course, phi x is finite. At this boundary, we choose the no source boundary condition. In this case, then the m square and the theta, they have to satisfy some relation. Otherwise, the solution you could not have the solution which satisfies the boundary condition. The relation between the m square and the theta is nothing but just the condensation happens case. Here we use we solve the equation. Assume the phi x equal to 1 at the horizon because this is a linear equation. So we can take the any value at the horizon. Then at the boundary, here z equal to 0. We take the no source boundary condition. So the radial one shows the theta 0 equal to the 72.84. And the other two cases with the nodes. In this case, we think such kind of solution are unstable because this solution needs more energy. This is the fundamental one. So this is nothing but this solution gives you the critical magnetic fields. Once the magnetic fields beyond this value, then the condensation happens here. And here we choose the critical magnetic fields to the m square case. Here we have two comments. Usually, as I mentioned before, the stronger the magnetic fields usually destroy the superconductor. But there are several papers, which says the magnetic fields could induce the superconductors. Here, I mentioned two papers, right? And also there is some experimental evidence published in these two papers. We think there are more other papers. We just mentioned two here.
Yeah, but again, how is that? How can you induce superconductivity just with a magnetic field?
Oh yeah, this is such kind of happens only for the p wave case. S wave case could not happen.
Yeah, of course.
So yes, right. And from maybe this paper, we realize that it says the lambda level has some the spatial coupling with some the magnetic fields, so it changes the states. We are not sure, very clear about this point.
Yeah, but when they say high, but for sufficiently high will be killed, superconductivity will be killed.
Yeah, yes, usually like that one.
Okay.
In the traditional model is this.
Yeah, okay.
But here the imaginary fields. I did not show the figure of these two papers, but is indeed when the imaginary fields increases, the condensation happens rather than destroy the condensation.
Yeah, I understand, but the question is that the more the magnetic field increases, the bigger the condensate. So it means that you cannot break superconductivity in that way, no matter how high is the magnetic field.
How high?
This is the issue.
Yeah, how high? I forgot the data from these two papers.
But that means that it's not important. There is no scale in the problem. So even if you have a huge magnetic field, still you are going to have superconductivity. That's what you are saying.
Yes.
Okay.
As the previous case is for the without the charge densities. It means the effect mass without we neglect this term. If this term appears, then the case with the non-Venetian charge density case, then the equation motion for the phi x tends to be this one. Okay. In this case, we have the three parameters: f square, e, and eigenvalue, and the lambda square. Lambda square is nothing but the charge density over the RH square, which is nothing but which is related to the Hawking temperature of the black hole. To solve this equation motion, we have to specify the one of the three parameters. Here we choose m square equal to the 3 over 4 case. In this case, En and the eigenvalue and the Hawking temperature, they will have some relation if the solution satisfies the boundary condition. If we choose the En as the lowest lambda level, in this case, here is the temperature, here is the magnetic field. Tc is the critical temperature for the case without the magnetic fields. You will see this is the normal phase, this is the condensate phase. The critical temperature increases with the magnetic fields. On the other hand, if we choose not the lowest lambda level, for example, take the eigenvalue is the positive value, then the critical temperature decreases with the magnetic fields. So this is quite totally different. Actually, also the vortex lattice solution or lattice also reliable in such kind of model. That's enough to consider the lowest lambda level state. In this case, the solution satisfies this one. Because the eigenvalue En is independent of the parameter P, therefore a linear superposition of the solution, you have this kind of case with a different P is also a solution of the model at the linear order. So according to this property, we could introduce the two functions, rho x write down in this way, rho y write down in this way, and introduce the parameter CL and A1, A2 are all parameters, constants. This just follows this paper. This paper considers the vortex solution in the normal holographic superconductor model. And here we define the difference between the rho x, rho y, defined in this way. Here we define the delta rho behavior like. In this case, the solution satisfies this one. Then the condensation, of course, depends on the boundary value of this one, or in other words, this term. This delta rho has a pseudo periodicity. This is the property of this function. Also, this one turn to be 0 at such kind of point. B1 and B2 are two vectors, satisfy this one. M and N are two integers. So if in the previous solution, if we choose A1 and A2 in this behavior, then this solution is nothing but just the triangle lattice solution. Here we choose the figure here. We choose the operator, dual operator. This is the J minus case, Jx minus Jiy. This is the dual operators. This is the profile. This is the counterform. This is just the triangle lattice solution. Of course, here we just assume the A1 and A2 is this way. If we want to show this is the Abrikosov solution is really the fundamental state, we have to consider the high order to make sure the free energy is the lowest one. Yes, but here we did not do that.
So here you want to prove that you have this solution.
Yeah. That's true.
It might be other solutions.
Yeah. This way. Here I have comment. Actually, last year, Pu Yan and Johanna Edmark and Schock and his student for the paper. Similar phenomenology is found in this model. This is a vector condensation and the triangle model also realized in the Einstein SU2 gauge fields. But with the magnetic fields of the magnetic component of gauge fields get larger beyond the critical value. But in this case, the magnetic field is not the electromagnetic, but is SU2 one. So in some sense, this model like the gluon condensation in QCD theory. But the the behavior to model behavior similar, right? Okay, here is my conclusion. We present a holographic model of a p-wave superconductor in the Einstein, Maxwell, and complex Wickes series. Through the numerical solve the equation motion, we found that this model contains a rather rich phase transition. Depend on the mass and charge of the vectors. There are zero order, first order, second order phase transition could happen. Also, the retrograde condensation also will happen in some regions. And also, the vector condensation could induce by applied magnetic fields. This is mainly due to there's no minimal coupling between the vector and the background gauge fields. And in this kind of model, the Abrikosov vertex lattice structure forms in the plane which is perpendicular to the magnetic fields. Actually, this is just the initial stage of a model. There are a lot of the works to do to discuss the various property of this model. Okay, thank you very much.
Any question?
Yeah.
But the vortex lattices, is it a triangular shape or the square shape? There's always discussion which shape of the vortex lattices takes. Depends on interactions.
Yes.
So in Pele superconductor, people expect to get square shape, not triangular shape.
Yeah. Here, yes, you're right. Because there are a lot of shape could be. Oh, sorry. How to? Here we just the shape crucially depends on the parameters A1 and A2, right? So we take these two values. Actually, this is an assumption. We did not prove this is true the fundamental state. Other shapes maybe is possible, but I think as you mentioned, other shapes I think this model also included. I think. Yes. We just make that. If we take the value of this one, then we get the triangle lattice.
So, what's the vorticity for this vortex solution?
Sorry.
Vorticity, maybe it's difficult to see from this construction.
Oh, I see.
Vorticity is the n. I mean, you have some solution which
Oh.
is like e to something. So vorticity is some n. I think you are working with vorticity 1.
Oh, yeah.
So you can put some integer and then you get other type of.
I see.
Okay, so if there is no more questions, thanks again, speaker.
Mm.